2, 4. So a learning process, this is something we have seen before. Where if you have some time series YT, you can write that time series as YT equals sum k equals 0 to infinity, size of k, x of t minus k. Now, while x is any other process time series, we assume that that process is also stationary, has a mean of 0, something like that. So if we treat x as our usual white noise, white noise means the mean is 0. Variance is 1. So I could write YT as some k equals 0 to infinity, psi k epsilon t minus k. And that should remind you of something. It is an MA model specifically, which can't. That's my favorite. Is it MA1?
I think it's MA3.
MA3, what made you think that this is MA3?
I just remember with one of the higher numbers.
Let me watch it this way. Maybe it's MA cubed, both k. Still don't get it?
Oh, it's MAK. Like
MAK, it's MA infinity.
Oh, yeah.
Right, that's an MA infinity process, and we've been over this that you can take any process and express it in terms of MA infinity. This goes back to that example that I used. What you are as a random person today is merely a linear combination of noise. Right? So where epsilon t is just noise. Think of it that way. It's not added in the same with the same weights, but those weights differ. The condition for those weights is that if you sum all of them, the absolute value, it must be less than infinity. It's the same as saying psi k approaches 0 eventually. So it doesn't have to be monotonically decreasing, which is why we use this. It's called absolutely summable.
Such a cool name for such a.
Absolutely summable psi k simply means that if you take the absolute value of psi k, sum them all together from 0 all the way up to infinity, the resulting value is finite. It doesn't have to be 0 or, some number, but it should be finite. That is the requirement. For YT to be stationary. Okay. In our case, if I take that expectation, this would simply be expectation sum k with 0 to infinity psi k epsilon t minus k. You can pull the sum out. And that is a property of expectation. You can always pull the sum out of an expectation. Psi k is a constant, so can I pull out psi k?
Yep.
What would that reduce to? Sum k equals 0 to infinity psi k times expectation epsilon t minus k. What is it?
Yes.
It is 0. Because all expectations are IID white noise, or all epsilons are IID white noise, so that would be 0. So the expectation of that linear process would also be 0.
Just like my plans for later today. Jesus.
I just love it.
I wasn't expecting that. Yeah, I really don't have anything planned for later today.
We know what the covariance is. Covariance is simply YT common YT plus H. Now, YT is sum k equals 0 to infinity. Psi k epsilon t minus k. Yes. I can't use the same index for the next sum, so I'm going to use m equals 0 to infinity, which would make it psi m epsilon t minus n, plus I'm adding plus h, so
Why can't you use the same?
because they are different processes. Remember when we had covariance of ax plus by comma cx plus dy from long time ago?
Vaguely.
Vaguely. Yes. Because there we had the same x's and y's, but we changed the values of the constant. They could be anything. But if you look at this, we're saying we have a series that is composed of epsilon t and lags of epsilon t. Over here, it is actually t plus h. So we're actually talking about another series. So sum m equals 0 to infinity. We can pull the sum out of covariance like we always do. Now, earlier I mentioned white noise variance as 1. It's a typical case, but let's keep a general value. Let's change that variance to be equal to sigma squared. so that we get a generic expression. So mean is 0, variance is sigma squared, not 1. Change that 1 to sigma squared.
You mean in the earlier notes?
Yeah, earlier today. Epsilon T, I wrote it as white noise, and I said mean 0, variance 1, which is a standard case, but let's generalize it and keep it as sigma squared so that we can use this formula for anything.
Okay. I haven't seen one word that Harris.
Can I pull the coefficient psi k, psi n?
Yes.
Yes.
It doesn't matter how you order it once you pull up and down, right?
Yes, it doesn't matter. Correct.
You managed to use
No. That's noise. That's also noise. And we know that noise can only be correlated with itself. So sum k equals 0 to infinity, sum m is equal to 0 to infinity, psi k, psi m. Going to rewrite the second part, t minus m plus h as t minus of m minus h. There is a reason why I'm writing it that way.
You're gonna do substitution, right?
Yeah, but how do we do substitution? So remember, we can't do substitution, nothing wrong with that. These two would produce a value of sigma squared, a non-zero value, under one condition. And one condition only. What is that one condition?
Is that when they're equal?
What should be equal as?
The K and the M by a.
So these two must match up, right? If they did for some value of m and some arbitrary value of h, then that would be non-zero. Otherwise, it's going to be 0 for all other values. So that sum is non-zero when k is equal to m minus h. Now, if I did that, would I need two sums? Change k equals m minus h. Would I need two sums? Because psi k would turn to m minus h. Psi m is just psi m. Those two, they're going to match, which means will become sigma squared. Will I be needing two sums?
Can you repeat that? Sorry.
When I do the substitution, the term in here would become psi n minus h for psi k, psi m, and covariance of epsilon t minus k, comma epsilon t minus k. Correct? Those two are the same, so that would be sigma squared. So everything that is inside that double sum reduces to this, right? Would I need two sums? One in terms, one running for m and the other for k?
No, no.
No, because there is no k more. So that would simply reduce to sum n equals 0 to infinity psi m minus h sigma squared. So we ended up getting this nice little expression for psi h. But we also know that since gamma h is symmetric, if I change this to be negative h, I can change it to positive h, correct? So it is a matter of choice as to how you want to keep it. So for any linear process, the covariance function is given by that. Good? Okay.
For some reason, when you wrote that, I was
Here I have a series, epsilon t plus 0.1 epsilon t minus 1.01 epsilon t minus 2 minus 0.001 epsilon t minus 3, and so forth. Of course, this is an MA infinity. Let's see if you remember something. This came from, I take that back. Because there's a minus, it did not come from an actual autoregressive process. So I take that back. So that is an MA infinity, and gamma naught, gamma 1, gamma 2 is what needs to be calculated. I know the standard expression, so m equals 0 to infinity, psi m minus 0, which is psi m also. Which will give me psi m squared. So sigma squared, psi 0, psi 1, psi 2, psi 3 are the only values that I know. And so all the other values are going to be 0, because I'm going to approximate the values. In practice, we'd probably have more than just 4 values. Like here, well, I've got this 4. So 1 squared plus 0.1 squared plus 0.01 squared plus minus 0.001 squared. Going to terminate it right there. So approximately equal to, because I do not know what we have past that point. You can use your calculator and tell me what you get. So 1.01 repeating. So approximately sigma squared. So the variance of the series is approximately equal to the variance of the noise, which is more likely to make the series more of noise than just some signal. Now we want to find gamma 1. I'll do gamma 1 and we can do gamma 2. So gamma 1 is sigma squared, 0 to infinity, psi m, and psi m minus 1. Yes.
What happened to the 1.1 when you?
I'm approximating it. So 1 times sigma squared.
Okay, I'm sorry.
No worries. So that would be minus h. Now, since we're going it's in positive flags in the sense our sine A's are positive flags, I can change that -1 and write it as do you agree? Because of symmetry of the autocorrelation function, covariance function. So they are the same. Now I can use m equals 0, 1, 2, 3, 1, 0. So psi 0, psi 1, psi 1, psi 2, psi 2, psi 3. Everything else will be 0. Do you agree? Because all we have is up to psi 3. Going to use approximately equal to sign here. So we know psi 0 is 1. 1 times 0.1 is 0.1. Psi 1, 0.1 times psi 2, 0.01. Psi 2, 0.01 times negative 0.001. So this
Yeah.
1
Oh, wait, no,
can't be 1. It's probably 0.1.
no.
Slightly less than 0.1 because we are taking away something. So it's 0.10099. So approximately 0.1 sigma squared. Good. Let's go ahead and find gamma 2. 0.01. Yeah. So gamma 2 is sigma squared m0 to infinity psi m plus 2, which I can approximate with finite number of psi weights. So psi 0, psi 2, plus psi 1, psi 3. That's the best I can do. Anything past that point would be 0. So psi 0, psi 1, excuse me, psi 2 is psi 2, plus psi 1, psi 3. When you plug in the values for the size, what do you get?
0.0099.
Which I can call it 0.0001 sigma squared.
Equals 0.0.
Oh, 0.0199?
No,
0099.
Oh, I see. So approximately 0.01 sigma squared. Now we have gamma naught, gamma 1, and gamma 2. How do we find rho naught, rho 1, and rho 2?
would it be the same way you find the MA?
Yes. So to find the autocorrelations, all we have to do is divide the gammas by gamma naught. So naturally, rho naught would be gamma naught over gamma naught. We get 1, as always. Rho 1 would be gamma 1 over gamma naught, which would be 0.1. Rho 2, gamma 2 over gamma naught, get 0.01. Correct. Now, if you, I don't want to use R to plot this. If you graph it at 0, we've got 1. Yes. At 1, I have 0.1. And at 2, I have a value really, really close to 0. I have point O1. What kind of model that does that look like? We're using an autocorrelation plot, and that's what it looks like. So what would be an appropriate model here? So autocorrelation function plot is used to identify the order of moving average models. Partial autocorrelation function plot is used to identify the order of autoregressive models. So if I look at this, that becomes sort of insignificant below that blue line. So you may say, okay, that is going to be an MA1 model. So all of these are unnecessary. Does that make sense? Yeah. So we pretty much found a relationship between the covariances and the cyclings. Right? So in a recursive manner, if you know the covariances, then we can find these values. Correct.
You said that it's basically an MA1 model because the 2 is just so small, it's kind of.
Exactly. So if you know the covariances, then you can sort of use an equation like this to find the values of the MA model. Does that make sense? So any linear process can be expressed, any time series can be expressed in terms of sine waves using what we just did at the very beginning. I mentioned autocovariances are quite important in this class because pretty much everything that we do in time series is related to autocovariance and autocorrelation. Are we clear? So the covariances of the time series phi are given by those values. And the ACF plot showed that an appropriate model is MA1. Past the first lag, the values were insignificant. And we assume that epsilon t is white noise. We want to get them all. Let's see if we can do it. So we know that any process can be expressed as some m equals 0 to infinity psi n epsilon t minus n. So that is a linear process. Sometimes people call it a linear filter. One of the same. Now we also derived gamma h to be equal to psi m equals 0 to infinity psi m minus h. We can also have it as plus h. Matter of choice, but here, since we are using psi 0, psi 1, psi 2 as supports, better to have it as plus h. If we find the psi waves, then we have the model that we need. What do we know? We know one of the values of Fedek, which is psi naught. Psi naught is always 1. Do we agree? It's always 1. So let's start with gamma naught. Gamma naught would equal to psi naught psi 1. Psi 1, psi 2. And the next one would be psi 1, psi 3. I'm not going to bring that in yet. Psi naught is 1, so it simply has psi 1 plus psi 1, psi 2 equals gamma naught. The next value, gamma 1, would be psi 1, psi 2. Yes, psi 1, psi 2. Psi 2, psi 3. Psi 3, psi 4, and so forth. I really am not going to worry about psi 3. Why?
It's gonna be way too small.
Why is going to be way too small? There is another reason.
You don't have a gamma 3.
Okay, we don't have gamma 3. What else?
We don't need it for this MA model.
We don't need it for this MA model, but why is that then?
Because it's 0.
Why is it 0? What made you think that it would be 0? Read the question carefully. It's in the question.
It's MA1.
It is an MA1 model, right? What is an MA1 model? An MA1 model has psi 1, psi 1. Even psi 2 is useless, correct? Because we have identified it to be an MA1. So that's all I need. I don't even need psi 3. So I'm going to ignore that. So I'm going to keep the first equation, gamma naught equals psi 1 plus psi 1 psi 2. Gamma 1 equals psi 1 psi 2. Yes? The reason being, I'm just going to assume psi 3 and above are 0. So psi k is equal to 0 for k greater than or equal to 3 because the model is MA1. By all means, I can set psi 2 equal to 0 also. So I'll start with the second equation. I have gamma 1 to be 0.892. And that is equal to psi 1, psi 2. Yes, the second equation. The first equation has psi 1, psi 2. So I can take this, plug it in the first equation.
The reason you're not making psi 2 zeros because that would kind of
That would not help us, estimate it properly. We will see what that value turns out to be. Even if you're looking for an MA1 model, let's just find the psi 2 and perhaps get rid of that psi 2 once we fit the model. We can do that. It's called model reduction. Psi naught is 1.29. Psi 1, psi 2 is 0.892, which would mean psi 1 is 1.29 minus 0.892.
With the 39.98.
Roughly. What do you have? 0.39?
Yeah, 0.398.
Good. Now that we have psi 1, we can find psi 2. So gamma 1 is psi 1, psi 2. So psi 2 would simply be 0.892 divided by 0.398. What is that? 2 point something?
2.14.
That's a large value. So, the series might actually end up being non-stationary. Can you tell me why? I don't know, but I'm sort of guessing. Perhaps this would end up being non-stationary. Any thoughts? Go back to the condition of a linear process. What should happen to the sums?
It should, when you add.
That fancy word, you said it was fancy.
When you add them all up, they should be.
Absolutely summable. So I'm guessing that this is not going to be absolutely summable because it sort of increases and perhaps it might get bigger and bigger. And when you add, it will not convert. It's a guess, I don't know. But at the end of the day, we're saying it is an MA1 model, so R fit.
So it is, or is it absolutely not?
Likely to be not, but I do not know, right? We can't simply come to a conclusion with two sides.
That would just be an outlier, basically.
Yeah, probably. So we know YC is epsilon t plus psi 1, 0.398 psi t minus 1. That is our hidden ball. Good. So in this case, we have a time series, Sloan time series, and we computed its covariances. The ASM identified MA2 as an appropriate model for whatever data, whatever series that produce these covariances. I'm going to assume epsilon t is normal 0. So we know what the model is. Let's see if we can fit it using the sine waves. Our standard expression, 0 to infinity, psi m plus h. That's what we derived today, and that's what we will have. But to solve for the size, gamma naught is psi naught psi 1 plus psi 1 psi 2 plus psi 2 psi 3. Good. Now, of course, we could put another term in, but I'm just going to wait and see, just like we did in the previous problem. Gamma 1 would be psi 1 psi 2 plus psi 2 psi 3. Yes? Psi 3 psi 4 would be the next term, but I'm just going to wait and see if I can solve it without that. Gamma 3 would be psi 2.
Wait, Professor.
Wait, he's not.
Would gamma not be gamma?
I'm sorry, I went too far, my bad. So gamma naught is psi naught, psi 0. Yes?
Yeah. So
Then psi 0, psi 1. Psi 1, psi 2, plus psi 2, psi 3.
that would be psi not squared, right? But seeing it's one.
Yeah, it's the same, it'll be 1, thank you. Then we would have the next case when h is equal to 1. I will have psi 0, psi 1, plus psi 1, psi 2, plus psi 2, psi 3. Correct? Gamma 3 would be psi 0, psi 3, plus psi 1, psi 4.
Are we skipping the M to?
Gamma 2, psi 2. Is that type 4?
Would it be psi 1, psi
Psi
2?
0, psi 2, psi 1, psi 3, psi 2, psi 4. Let's get rid of gamma 3. We'll just stick with gamma 2. Okay. Let's see if we can solve with what we have. I'm going to plug in gamma naught is equal to 1. Excuse me, psi naught 1. So I will have 1 plus psi 1, psi 2, psi 2, psi 3. The next gamma 1 would be psi 1, psi 1, psi 2, plus psi 2, psi 3. Yes? Gamma 2, psi 2, plus psi 1, psi 3. Good so far? Now, if you look at the second equation, that part and that part are one and the same. Yes? So I can rewrite psi 1, psi 2 plus psi 2, psi 3 equal to gamma 1, which is 0.8, minus psi 1. I'll keep it as psi 1 because we don't know what that is. Going to take this and plug it in there. Gamma 1 is 0.8. So I'm rewriting this equation and solving for this part. This part right here would equal to gamma 1 minus psi 1. Gamma 1 is 0.8. So I'm going to take this, plug it in the first equation. So I know that expression is equal to 0.8 minus psi 1. So if I rewrite gamma naught is 1.24 equals 1 plus 0.8 minus psi 1. So 1.24 equals 1.8 minus psi 1, which would imply minus 0.56 equals minus psi 1. Therefore, psi 1 equals 0.56. Good. Now, since we sort of identified it to be an MA2 model, all I need is up to psi 2. So I can say psi 3 to be 0. If that is the case, that would become 0. That would become 0, but whatever we did will not change. Reason being, that would become 0. That would become 0. The equation will remain the same. Does that make sense? So at this point, for me to carry psi 3 with me, But the process is going to make it more complicated because I have to solve another set of equations. But if I make psi 3 to be 0, this equation, whatever we derive, would still hold true. Because this would become 0, that would become 0. Algebraically, we'd be doing the same thing.
Maybe you just, wouldn't that just make gamma 2 equals psi 2? Because
We can do it that way too. So I'm going to ignore gamma 2 also.
Okay.
Right? Because I don't want psi 3, so I can just ignore gamma 2 also. And simply use psi 1. So gamma naught would be equal to 1 plus psi 1 psi 2. We found the value of psi 1, which is 0.56 psi 2. That's gamma naught. What is gamma naught? 1.24.
It's just psi 1 psi 2 plus psi 2 psi 3.
I'm making psi 3 0.
Oh, you're
So right. So 1.24 would be equal to
1 plus 0.56.
1 plus 0.56 psi 2. So 0.24 would be equal to 0.56 psi 2. Therefore, psi 2 would be 0.24 divided by 0.6.
0.43.
0.43. Good? Yes.
Oh, actually, no.
And you said we're just gonna ignore the gamma 2.
I'm going to address that.
Okay.
So our model simply becomes yt equals epsilon t plus psi 1 0.56 epsilon t minus 1 plus psi 2 0.43 epsilon t minus 2. Right? I gave you all the extra covariances so that you can see that we don't need all covariances to find or to fit the model. I am terminating at gamma 1 because if you look at an MA2 model, all we need is rho 1 and rho 2, right? In this case, since I have gamma naught and gamma 1, I can use those two equations to find psi 1 and psi 2. Does that make sense? You need only two equations to solve for two unknowns. And of course, I'm making the assumption for psi 3 is 0. Are we clear? Yes? Now, had I given rho 1 and rho 2, then we should start with rho 1 and rho 2 equations. Does that make sense?
So, like, can you repeat the last bit?
Huh?
Can you repeat the last bit?
If I just gave you rho 1 and rho 2, then we'd probably have to go with, these two equations because we do not have gamma naught. So you can see this process sort of is a recursive process. In the previous problem, we took the second part, plug it in the first part, and then solve for the coefficients. So if you have more model parameters, the process would simply involve looking at all the autocovariances and solving for size in a recursive manner.
And this stuff is the last stuff that's gonna be on the
This is the last step of the example. Good? Do we follow? Okay? So that is our final MA2 model. Good? So on an exam, If I have this problem, I will not give you gamma two. Right? Or if I'm giving you autocorrelations, I may or may not give you gamma.
Can you give us the same exact example on the exam?
It depends on you. That would defeat the purpose of the exam. But do we understand that?